Bismillahirrahmanirrahim. In this lecture 10C of real statistics, we will discuss the central concept of causation. As opposed to this, the central concept of nominal statistics is correlation. There is a huge amount of confusion related to the concept of causation in philosophy, in science, in econometrics, and so we will just give some basic background information to clarify this. We will take the very straightforward approach to causation developed by Woodward in this book called Making Things Happen. And basically it turns on what we use causation for. And we use causation to learn how to change things. So basically, from this practical point of view, causation is about how we can use changes in X to affect changes in Y. It is known from growth studies that children in animal have the ability to learn causation, then they seek causal effects and they learn them and they learn to use them. So it is very surprising, and this is the source of all confusion, that actually causation cannot be deduced from observations. So how do children learn causation if it cannot be observed? Basically because some aspects of knowledge of causality is built into our minds. And because of this pre-existing knowledge, we are able to look at the world and deduce the existence of causes. The knowledge that we are born with is the idea that everything which happens because of a cause. This is knowledge that is built into us. It is not really part of external reality. This comes as a great surprise to people because we are used to thinking about the existence of causes. We see them happening every day. And so we think that this is part of external reality. But people who have thought more deeply about the nature of knowledge have realized that this is not really part of external reality. If we just look at the appearances, we cannot be sure that something is the cause of something else. We can only see that I light a fire and then a smoke appears. But the fact that the smoke is caused by the fire is not part of the observed reality. Next time I light a fire, maybe there will be no smoke. Maybe this could happen at random. The fact that this is not this way is part of the world, but it is not something that is necessary part of the world. If sunrise happens every day, it's not necessary that it will happen tomorrow. So the positivist philosophy basically says that causality cannot be observed and therefore it doesn't exist. Now this is very deep and complex, and it's not expected for the student to understand this on the first pass, but we just explain why there has been such confusion regarding causality. What we can see in the world is systematic sequences of events, but what we cannot see is the underlying forces which drive these events. For example, the force of gravity. So knowing that there exists a force of gravity allows us to conclude that the apples will continue falling just as they have in the past. To understand this better, consider a sequence of numbers like 7.1, 8.0, 8.9 and ask, what is the next number? Well, there is a pattern in these numbers that they are increasing by 0.9. So we might guess that the next number will be 9.7 or 9.8. This is just a guess, and we have no reason to be sure of this guess. We are just looking at a pattern and then extrapolating from that pattern. On the other hand, suppose that these are measurements of weight of a baby girl at 4 months, 6 months, and 8 months. So the next one in the sequence will be the 10-month. And now, based on our knowledge about how children grow across the world, we can say that yes, we can expect about 0.9 kg weight gain on the average. So one guess based on a pattern doesn't have anything to support this. The other guess based on a real world underlying growth process is built upon a stronger and more solid experience, and that's why basically causality is at the deeper level. There is a cause for the increase in numbers, and the cause is that children grow when they age, and this is a deeper pattern than what is apparent on the surface. So the causal patterns that we see are quite complicated, and there are lots of subtleties and technicalities, which is the reason why they have caused so much confusion, and we will try to pick up some of the essential elements necessary for the course. Of central importance to us is the concept of a direct cause. So it can happen that X causes Y causes Z. In this case, X is part of the causal chain, but then immediate cause, that if I do X, it leads immediately to Y, that is a direct cause, and those are the building blocks of more complex causes. So even when you come to a direct cause, there are two types. There is a deterministic cause, which means that when X changes, then Y changes. So this is like the fire and smoke, or this has means that if we look at the whole configuration of variables that we are studying, then it is possible to change X and bring about a change in Y when the environment is appropriate, when the other variables are fixed at some certain values. So this is a complexity, because basically we need to keep the environment fixed in order to make sure that it is the change in X which is causing the change in Y. And a second complication is that of a probabilistic cause. So, for example, smoking leads to cancer. Now, this kind of thing, it is not guaranteed. Lots of people who smoke did not get cancer, but basically the probability of cancer increases from almost near zero to a much higher probability. So instead of saying that X actually changes Y, changes in X cause changes in the probability of Y. So for an example, if you are vaccinated against COVID, then your probability of catching the infection becomes less. So suppose that we have two cases, if X is 0 and there is no vaccination, your probability of catching COVID is 60%. After vaccination, it becomes 20%. So one very important thing about probabilistic causation is that you can only observe it at the group level. You cannot see it for individuals. So if you have 100 people and no vaccination, you find that 60 of them get COVID. If you have 100 people with vaccination and you find that 10 of them get COVID, then you have a probabilistic cause. But if you look at any one person, it is possible that he has vaccine and he also has COVID, or he has vaccine but no COVID, or he has no vaccine and he got COVID, or he has no vaccine and he didn't get COVID. So all four types of cases are possible. So when you look at individuals, you cannot determine cause. You can only determine probabilistic cause when you look at large groups. Probabilistic cause includes deterministic cause as special case, where the probability of the change is 100%. So now we are going to give a little bit of a technical definition of causation, direct cause. So I have variables x, y, and then I have other variables z1, z2 up to zn, which are we all under study. Then we say that, okay, fix all the variables, the z's, the extra variables, at some particular values, and then change the value of x from the observed value to some other potential value. And when you change x, if this causes a change in y, or if this causes a change in probability of occurrence of y, then we say that x is a direct cause of y. Now, this should be true for some configuration of values and for some sets of values. It may not be the case that all changes in x lead to changes in y. Some changes in x could be such that they don't affect y. And similarly, it should be true in some configurations. It's possible that for some configurations, some settings of z's, x has no effect on y. The z's could block off. But at least for some settings, x has to be able to affect y as long as they are constant at some fixed values. And so this is the probabilistic cause. And note that this cannot be detected by one example, but we need to replicate this study for several cases and see that what happens to y when x changes. And if we find that the probability of y occurrence changes, then we will say that x is a direct probabilistic cause of y. Now, if x affects y through a variable, so x causes z, x is a direct cause of z, and z is a direct cause of y, then x is not a direct cause of y. And how do we see this? Well, if we fix z at some value, at any value, then x will not be able to affect y, because the only way that x affects y is through its effect on z. So it is said that z screens off the effect of x on y, and conditional on z, x and y are independent. It is worth noting that x, y, and z need not be random variables here. So the concept of independence is not tied to random variables. One of the people who has done the most to elucidate the concept of causes is Judah Pearl, and in his terminology, if x is a direct cause of y, we say that x is a parent of y, and if x is an indirect cause, which means that it is linked by a sequence of causes to y, then x is a causal ancestor of y. And given a system of variables under study, if x is an ancestor of y and changes in x cause changes in z, when we hold all variables not on the causal path to be constant, then x is called an indirect cause of y. This definition takes care of very complicated cases, which we will not be discussing in this course. Now we'll look at some consequences and implications of these definitions of causality for practical issues related to data analysis. We can define real statistics and differentiate it from standard conventional orthodox statistics by saying that real statistics is about the search for causal links. In particular, it is about the search for direct causes, because all causal chains are built up of these units. So you can't understand causality until you understand direct causes. Now, what is a direct cause? If x directly causes y, this is not a relationship between variables or between numbers. This is a mechanism in the real world which operates, which is such that if you change x, then it has an effect on the variable y. Either it directly changes it or it changes the probabilities of outcome. So when we are searching for causes, we are searching for some mechanism which exists in the real world. Because causation requires holding other things constant to make sure that the effect is due to x, this thing may not be achievable. So there's one way to think of causality is to think of a hypothetical change. What would have happened if we had changed x while everything else remained the same? Because of this counterfactuality, the causality cannot be observed. One of the things that is worth noting is that the concept of direct cause cannot even be defined and differentiated from indirect cause in the language of statistics and econometrics. So the fundamental goal of real statistics cannot even be stated or understood within conventional statistics. So this chapter is about explaining why regression is a failed methodology, and the key aspect is that basically regression statistics, econometrics study correlations. They fail to distinguish between direct and indirect causes. There is no concept of causal pathways. There is no notation, symbolism, conceptual framework for discussion of causes. Causation itself is not in the numbers. It is always there in the real world structures behind the numbers. Do real statistics. Basically, we have a collection of variables that we want to study. We don't go in with a blank mind because there's so many different kinds of causal chains that are possible that it's not possible to start from scratch and discover causality. Instead, we go in with some hypothesis about the causal connections between these variables, and then we assess to see if the patterns of correlations that we can observe match our initial hypothesis. And causal hypotheses often have predictable implications which go outside the range of the observed data. So we have to look at what these are, and then we have to go and assess them. And this will often involve expanding shoe leather, that is going out into the real world and seeing whether something predicted by our causal hypothesis is happening. If, as will often happen, our original causal hypothesis fails to be true, this will help us in the way in which it fails will help us in formulating alternative causal hypotheses. So to explain how all of these abstract concepts work in real world examples, we look at a specific example which has to do with a data set in which we look at housing prices per square feet and the number of shops in the neighborhood of that house. The data set is pictured in this graph. The blue dots are the housing prices per square feet. On the x-axis, we have the number of shops. So at 0 shops in the neighborhood, we have a lot of houses, and then at 1 shop and 2 shops, and finally we have 10 shops. So if we look at the cluster of dots, each dot represents a house, and the dot is actually the price per square foot of that house. So we see a slightly rising trend. And actually you can run a regression, and the regression has been run. And according to the regression, this is a very significant result. And you can say that price is equal to 27.18 plus 2.63 times the number of shops. So basically, as the number of shops increases, the price of the house increases in square foot. That is what a regression analysis would tell you. But first of all, the regression line is derived under hopelessly false assumptions. And the other thing is that the causality has been assumed without any discussion or justification or understanding of the real world. So this is the problem with conventional regressions. It doesn't actually tell us anything. Instead of running regressions which always deceive us, it is much better to to directly look at the data. So here is an attempt to directly look at the data. For each cluster, you have the numbers are 1, which means 0 shops, 2 means 1 shop, and so on in the neighborhood. And the blue bar is the median price per square foot of the house. So you can see that as the number of shops increases, the median price shows an increasing trend. The orange line is just the number of houses in that neighborhood. So in the first cluster where there are 0 shops, there is about 70 houses. And then in this declines, so there are about 20 houses in which have 3 shops in their neighborhood. And then at 4, or which is at 4 indexed, we have more, about 45 houses, so on. So basically the number of houses is zigzagging, but it declines as you increase the number of shops. So in the highest category, which is 10 shops in the neighborhood, you have very few houses, like 10. So this is what the data is directly without any regression, and basically this is all the information the data is giving. The regression line does not add anything. In fact, it adds false information and leads to false understanding of what the data is. So basically, if one ran the regression, one would, and students often would run this regression, and they would come to the conclusion that if you have more shops in the neighborhood, that leads to higher housing prices. This is simply a false conclusion because this is a causal conclusion, and causal conclusions cannot be made from correlation data. So regression analysis stops at the first diagram, but actually real statistics starts from here. So we see that there seems to be a pattern. Housing prices rise with the shops, and this is a clue to something which is happening in the real world which causes this to happen. But now we must explore the real world. What is the cause of this? So if two things are correlated, then the basic three hypotheses are either X causes Y or Y causes X, or there is a common cause for both of them. So all three of these possibilities exist. We see that there is a pattern. There is a pattern that when the number of shops increases, the housing prices also increase. So there is a correlation between number of prices and housing price per square foot. What is the reason for this? Well, one hypothesis is that people would like to live in houses which have convenient shopping, and so there is high demand, and this leads to a rise in price. So this would justify the idea that more shops lead to higher demand for houses and lead to higher prices. But there is the converse hypothesis also possible, that maybe people who live in expensive houses attract more stores near them. So there is a rich part of town and a poor part of town. The rich part is always a small part, and in the rich part you have more stores. So basically the number of shops increases because more shops want to locate in places where there are rich people. There are also some other possibilities to explain this pattern. Maybe, for example, there is the geographical structure of the town. Suppose the town is built around the lake, and the lakefront properties are very expensive, and that's where the tourists also come, so the shops also locate there. So here we have a situation where there is a strong correlation between housing prices because the expensive houses are all lakefront, and there is a strong and the shops, the number of shops is also very high in that same neighborhood, but the shops are not actually catering to the town, they are catering to tourists who come to the lake. So there is a accidental correlation between the two. And there are many other things which are possible which would explain why housing prices rise. So when we look for causes, just the numbers, just the data on housing price and shops cannot tell us about the causes. And that is why real statistics cannot be done by just looking at numbers. So among all of these causal hypotheses, how would we find out? Well, we have to expend shoe leather. We could go and ask real estate agents that what do people look for in houses? And if we ask them that why are housing prices so different, why are in this area where there's lots of shops, why are the housing prices so high? The agents could tell us that this is because people are searching for convenient shopping, or they could tell us some other reason. Real agents have a lot of experience in selling houses, so they would have knowledge of why housing prices are high. We could also ask home buyers that what do you look for when you're purchasing? Do you look for convenient shopping, or do you look for other factors? We could ask shop owners, why did you locate your shop at the current place? And some data, we could look at the shop to see if there is a newly located shop, does it cause a rise in prices at later points of time? So all of this investigation of the real world leads to real knowledge, as opposed to this playing with numbers and mathematical formula leads to the illusion of knowledge. You get the idea that by running fancy regression on data, you're getting some knowledge, but in fact all you're getting is an illusion. So some of the key lessons that we take away from this example is that in order to learn about causes, you have to think intuitively what is happening in the real world. And then basically, if you're trying to find out the direct effects, then you have to look at big effects and small effects. Small effects are difficult to detect because they're generally due to indirect cause. So basically we have to think about direct causes, and when you have a direct cause, you can usually detect the effect. When you see two variables which are correlated, then you have to think of these three hypotheses. And this is not all. There are more complex ways that variables can be correlated um, without being actually causally related. And we have to think, in addition to these two variables, what are other relevant factors, because they all matter. You have to keep them fixed in order to assess whether changing S will cause changes in Y.